Hello everyone, this is SANIYA.G.S from Bangalore Institute of Technology. I am currently in second year of engineering from Computer Science and Engineering department. Today I have got the opportunity to discuss and share my knowledge on the topic called cache memories as well as mapping functions. So let's start the video. So first of all we will learn what are all the things we will be covering in this video. So in this video, we are going to learn what are the cache memories, introduction to cache memories, what are the characteristics, advantages as well as the disadvantages of cache memory, and what are the levels that are seen in the cache memory. And there are other two topics called as cache hits and cache misses. So which describe about how data is stored in the cache memories. Later on we will be moving on to the mapping functions, types of mapping, advantages and disadvantages of types of mapping, and the comparison of the mapping functions what we have defined before and the impact of those on cache memories and the example of mapping function usage, and we will be finally moving on to the conclusion. Let's start a video. So let's learn what are the cache memories first. Let us learn what are cache memories. These are very small and very fast temporary memories. So in this cache memory, the data is stored temporarily stored, that is volatile. When the power is turned off, the data is erased from the system. That is called as a cache memory. This is a temporary memory and it is very small. The size of the cache memory is very small and the data accessible from the cache memories is very high speed, and these memories are used to faster process the data. The cache memory is present between the CPU and the main memory, and the correspondence between the main memory blocks and those in cache is specified by a mapping function. So the use of mapping function is that we can understand the correspondence between the main memory and those of the cache memory. Let's understand the introduction to cache memories. Cache memory play a crucial, a very important role in the performance of a computer system by providing fast access to frequently used data. As I said before, the accessibility from the cache memories is very high. It is a high-speed storage layer that sits between the processor as well as the main memory, and the future sections will provide an overview about the different mapping functions that are used in cache memories and their impact on the cache performance and the real world examples of their usage. Let us learn about the characteristics of cache memory. Before that, we should be knowing RAM, which is a random access memory that is used as a main memory, which is also volatile. So as I said before, the cache memories are also the volatile memory. So let us learn even the differences between the RAM as well as the cache memory. So let us also learn the characteristics of cache memory. Speed, the access time is very fast than main memory. The main memory is the RAM. So the accessibility of data is very high in the cache memory compared to the RAM. And the cost, it is an expensive memory compared to RAM. The cost of the cache memory is a bit high, and the size is very small compared to the main memory. The proximity, it is very closer, as I said, that is in between the CPU as well as the main memory. So the cache memory will be nearer to the CPU compared to the main memory. The volatility, it loses its content when the power is turned off, and it is a temporary memory. And we will see a lot of levels in the cache. So in modern computer system have multiple levels of cache like L1, L2 and sometimes even L3 with different capacities, and cache management is handled by the computer's hardware and software to ensure efficient utilization and data retrieval. Associativity, cache memory can be self-associative, directly mapped or fully associative, defining how data is stored and retrieved. So these are the types of mapping functions. So that is the use of mapping functions. So we are telling how the data is stored and retrieved from the cache memory. For that purpose, we are using the mapping functions. Now We all know the characteristics of cache memory. What is a cache memory? How the data is retrieved? What are the different types of mapping functions that are used? So we all know what is the main benefit of the cache memory. That is a fast data retrieval. So except that function, the fast data retrieval, why the cache memory is used, what is the major advantage of cache memory? So it is used to access the data that is repeatedly used. So that is the main use of cache memory. If we have the program, there are certain set of instructions are to be executed repeatedly and frequently, which are used multiple times, and the remaining instructions are to be executed only once. If we consider a set of instructions, there are several instructions that are frequently, that means the multiple times they are used, and there are certain instructions that are only used once. So for that purpose, to retrieve the data which occur frequently, we use the cache memory. At this time, the cache memory play a very significant role. For example, analysis of programs shows that most of their execution time is spent in routines in which many instructions are executed repeatedly. These instructions may constitute a simple loop, the nested loops, we all know the loops, and which executes multiple times, right, until the condition is true. So at that moment we use the cache memory. It play a very important role when we use the simple loop, the nested loops, or even the system calls. Right, a system call is nothing but when a function calls itself, right? So that is called as a function call. I'm sorry, the system call. So at that moment we use the cache memory. The actual detailed pattern of instruction sequencing is not important. The point is that many instructions in localized areas of the program are executed repeatedly during some time or period. We call it locality of reference. So that is called as the locality of reference. They are so much faster than the memory and play a crucial role during the access of data and reduce the total average access time. For example, if we don't use the cache memory, when accessing the data, it accesses all the data, right? That means the set of instructions which are executing frequently as well as at once. So it actually increases the access time. So by using cache memory, we reduce the average access time by only accessing the data which is frequently occurred. Now we all know what are the advantages of cache memory. Let us even know what are the disadvantages of cache memory. The first disadvantage is cost. The cache memory is more expensive compared to the main memory because of its specialized design. It is very small and even faster, right? So it has a specialized design. The cost of the cache memory is very much higher compared to the main memory, and it has a limited size. A cache size is very restricted and we cannot extend that size. So it is very too small. It might not effectively enhance overall system performance. It only enhances only little bit performances like the access time and all, but not the overall performance of the system. This is the another disadvantage. And the complexity in design, managing cache coherence especially in multi-processor systems can introduce complexity to the overall system architecture. So there is even the complexity is very much higher in the cache memories. The other disadvantage is that it is a temporary memory, right? We cannot use it for the storage of data permanently. So that is the another disadvantage of the cache memory. So let us learn about the levels of cache. There is first the level 1 cache, which is actually located directly on the CPU chip. As you can see here, it is directly located on the CPU chip. The size is very small in size, often ranging from few kilobytes to few megabytes. The purpose of this level 1 cache is rapid access for instructions and data directly used by the CPU, and the speed is extremely fast, providing low latency access. This is about the level 1 cache, which is actually very nearer to the CPU, as you can see in the diagram. So next we are moving on to the L2 cache, which is the level 2 cache. The location is, it is positioned between L1 cache and the main memory, as we can see here, and the size is larger than the L1 cache typically. ranging from few megabytes to tens of megabytes, holds additional data and instructions for the CPU and acting as a buffer. Buffer is also like the storage, where the temporary data is stored. So the level 2 cache act as a buffer, and the speed is slower than L1 but faster than accessing main memory. So this is about the L2 cache. Let us move on to the L3 cache level. And now the L3, the level 3 cache, the location is shared among the multiple CPU cores or processors. The size is larger than the L2 level cache, often in tens of megabytes or more. The purpose of the level 3 cache is it serves as a shared cache for multiple cores, facilitating inter-core communication. The speed is slower than L2 cache but faster than the accessing main memory. So we have seen the three levels of cache where the location, the size, the purpose, speed, everything is different. So these are the three levels of the cache. Each cache level operates in hierarchy with goal of providing the CPU with fast access to the frequently data and instructions. All the three levels of cache mainly focuses on the fast access to frequently used data as well as the instructions. The hierarchy allows for a balance between the speed, the capacity as well as the cost, optimizing the overall performance of the computer system. So that is the goal of these three levels of cache. Here is the another new topic called cache hits. So this describes when the data is stored in the cache memory. What if that is not present in the CPU or the main memory while accessing? So this describes about that. So let us learn. The cache control circuitry element determines whether the request word currently exists in the cache or not. So this is a control which checks whether the word which is stored is actually present in the cache or not. If it does, the reader or writer operation is performed on the appropriate cache location. In this case, a read or write hit is said to have occurred. So this is when the data is actually present, for which data we are searching, that has to be present in the cache. At that moment, this process happens. Next, the main memory is not involved when there is a cache hit in a read operation. For a write operation, the system can proceed in one of the two ways. In the first technique called the write through protocol, both the cache location and the main memory location are updated. The second technique is to update only the cache location and to mark the block containing it with an associated flag bit, often called as dirty or modified bit. So this is the second technique. The main memory location of the word is updated later when the block containing this marked word is removed from the cache to make room for a new block, right? So when the word is removed to make the space for the word or the process. So this technique is known as the write back or copy back or protocol. These are about this is the information about the cache hits when the data is present, and the case is that when the word that we are searching for is not present in the cache. So far we have seen what if the word we are searching is present in the cache memory. What happens at that time? So we have seen the read will take place by only one technique and the write process will be taking place by the two techniques as discussed in the previous slide. Next we will be moving on to the cache misses. A read operation for a word that is not in the cache constitutes a read miss. As I said, if the word is present, that is going to play a hit process like cache hits. If it is not present, then it is going to perform the cache misses. It causes the block of words containing the request word to be copied from the main memory into the cache. If it is not present, it is making that the data which is not present to be copied from the main memory to the cache. So that is the function that is going to be performed by the cache misses, so that they will be copying the data from the main memory to the cache. After the entire block is loaded from the main memory into the cache, the particular word request is forwarded to the processor. After copying the data from the main memory, it is forwarded to the processors. And when a write miss occurs in a computer that uses the write through protocol, when a read is missed out, that is copied from the main memory. What if the writing process stands for the word which is not present in the cache? It is going to call the write through protocol. The information is written directly into the main memory. This is going to be performed when we are performing a write miss, when there is a write miss in the cache. For the write back protocol, the block containing the addressed word is first brought into the cache, and then desired word in the cache is overwritten with the new information, right? Next, for the write back protocol, the block containing the addressed word is first brought into the cache, and then desired word in the cache is overwritten with the new information. So this is about the cache misses. Next, we will be moving on to the mapping functions. What is the definition of a mapping function? A mapping function determines how data is stored and retrieved from the cache memory. So far we have seen how the data is stored in the cache memory, right? Like what is going to happen if you search a word which is there in the cache and which is not there in the cache by cache misses and cache hits. So now we will be moving on to a function, that is a mapping function, that determines how the data is stored and retrieved from the cache memory. It specifies the relation between the memory addresses and the cache entry locations. So this mapping function that is used to determine the relationship between the memory addresses and the cache entry locations. What are the types of mapping functions? There are various types, but here we will be mainly focusing on the three types. One is the direct mapping, fully associative mapping, and the set associative mapping. So these are the three types we will be focusing in the future slides in the topic called the types of mapping functions. Why we need a mapping function, right? So the understanding the mapping functions is essential for optimizing cache performance. So we should be knowing how the data is stored, how the data can be retrieved from the cache memory to maintain the high performance of the cache memory, and minimizing the access times to increase what is like how to use the cache more efficiently. We need mapping functions for that. For example, cache consisting of 128 blocks of 16 words each for a total of 2048 words, and assume that the main memory is addressed by a 16-bit address. The main memory address has 64K words, which we will view as 4K blocks of 16 words each. So mainly the mapping functions are used to efficiently store the data in the cache memory and retrieve the data from the cache memory, so which actually enhances the performance of the cache memory. We use the mapping functions for that. That is the main purpose of the mapping functions. Let us briefly understand the types of mapping functions. First type is direct mapping. Direct mapping is a memory allocation technique in the cache memory where each block of main memory has a unique location in the cache. So this is the definition of the direct mapping, which is very simple. So next, one-to-one correspondence. How the data is stored. So that we made up points based on how the data is stored in the cache memory. One-to-one correspondence. Each block in main memory directly corresponds to a specific block in cache. So the block in the main memory that is directly corresponding to a specific block in the cache. So that is about the one-to-one correspondence. Next we have simple mapping. This is a straightforward mapping scheme that uses the address bits to locate the cache line directly. That is a very simple mapping. This is a first type, right? So this is very simple compared to the other two types. The fast access. Of course, we use the cache memory for the fast access, but these are the functions that are being used to make it still more fastly accessible. Direct mapping allows for quick access since the mapping is direct and requires minimal time, and this is very simple compared to the other two. So here the access is very fast and minimal hardware for addressing. Next, the limited flexibility, the drawback. There is a drawback for the direct mapping. So what is the drawback for this? So the drawback is that if two blocks in main memory map to the same cache location, if they are pointing to the same cache location, conflicts occurs. So we have seen there is a unique a block in the main memory that is corresponding to the another block in the cache memory. So if there are like two blocks, not single block but two blocks that are corresponding, so this is where the conflict occur. This is the drawback of the direct mapping, leading to the cache misses and reduces performance. Cache misses as an, so we have seen the cache misses, right? So this triggers the cache misses and reduces the performance. So this is the drawback of the direct map. So let us see the example for that. If a cache has 8 lines, the main memory has 64 blocks corresponding to it. Each cache line directly corresponding to 8 consecutive blocks in main memory. So this is about the direct mapping, which is very simple and which is very fastly accessible compared to the other two mappings. So this is the block diagram of the direct mapping. Here we see the main memory where each block that is corresponding to the another block in the cache memory. So this is very simple and fastly accessible. Let us move on to the other type of mapping function. The next type is fully associative mapping. Associative mapping is a memory allocation technique where a block of main memory can be placed in any cache location. So in the previous type we see only a specific block has another specific block, but here there may be any block where the data from the main memory is stored. So moving on to the flexibility of this mapping, unlike direct mapping, any block of main memory, there is no specifically mentioned that only this block has to be allotted for that data. That can be any memory. So that is the flexibility, right? So we can use any block to store. There is no specific block for that that can be placed in any cache line. So offering more flexibility. That is, this is more flexible compared to the direct mapping. Tag comparison. Each cache line contains both data and a tag. During cache access, all tags are simultaneously compared to identify the block, allowing for parallel searching. Next, there are no conflicts. So as we seen in the direct mapping, that is a drawback where there are conflicts because if there are like two blocks corresponding to the same another block in the cache memory, the two blocks are corresponding to the same block in the cache memory, there is a conflict occurring, there is a cache miss occurring. So there are like conflicts occurring in the direct mapping, but in the fully associative mapping there are no conflicts since any block can reside in any cache line. So there are like no conflicts, which it has more flexibility. Next, hardware complexity. Associative mapping requires more complex hardware for attack comparison, making it more costly compared to the direct mapping. Moving on to the example, in a fully associative mapping cache with 8 lines, any of the 64 blocks in main memory can be placed in any cache line. There is nothing specifically mentioned here to store this block only in that block. It is nothing like that. We can store the data from the main memory to the cache memory in any of the blocks. This is the advantage of fully associative memory, but the disadvantage of the fully associative memory is that it is more costly because of the design, and it is more flexible. That is the advantage of this mapping. Let us move on to the next mapping function. Before moving on, let us also see the block diagram of the associative mapping. As I discussed, there can be any block corresponding to the any block in the cache memory. There is nothing specific in the associative mapping. The next and last type of mapping function is set associative mapping. Set associative mapping is a compromise between direct mapping and the fully associative mapping. Let us learn still more about the set associative mapping. Divide cache. The cache is divided into a number of sets, each containing multiple lines. Each set is similar to a small direct mapped cache. Block placement. A memory block can be placed in any line within its corresponding set, allowing for some flexible while still avoiding the full complexity of fully associative mapping. So this set associative mapping, there is a compromise between the direct mapping as well as the fully associative mapping. The flexibility and reduced conflict set associative mapping strikes a balance, offering more flexibility than direct mapping, which helps reduce conflicts compared to fully associative mapping. Since this is a compromise between the two types of mapping function, we see the flexibility of the the second type, the associative mapping. And what is advantages of the direct mapping? It is more, there is it has conflict, but this doesn't have any conflicts. That is the advantage of this set associative mapping. Let us know the example. In a two-way set associative cache with 8 sets, each set contains 2 lines. This means a memory block can be placed in of the any of 2 lines within its design set. So this is like the mixture of both the direct mapping and the fully associative mapping type. The tag comparison within a set, the tag comparison is done within the set, making it more efficient than fully associative mapping, but providing the more flexibility than direct mapping. So here we are modifying the disadvantages of direct mapping as well as including all the advantages of direct mapping as well as fully associative mapping. So this is the block diagram of the set associative mapping. Here we can see the mixture of both direct mapping as well as fully associative mapping. And here are the taglines which are set. So for the two blocks, we can set a single tag like that. So this is the set associative mapping. We have already seen the disadvantages and advantages of direct mapping and all the mapping functions, but still let us go to the overview of this. The advantage is that simplicity. Direct mapping is straightforward, making it easy, right? It is very simple, efficient in terms for hardware design. And the disadvantage is that it is a limited flexibility. It can lead to the high conflict misses that give rise to the conflict misses, as multiple memory blocks may map to the same cache set, so reducing the cache performance. This is the advantage of and disadvantage of the direct mapping. Next, the advantage and disadvantage of the fully associative mapping. The flexibility. Any block of memory can be placed in any each line. That is the advantage. And what is the disadvantage? Complex hardware. As you can see, it is very tough for the designing this mapping function. The complex hardware that requires an additional circuitry to search for a block in any cache line, making it more complex and potentially slower, higher access time due to the need for a search across all cache lines. So the access time may be longer compared to the simple mapping functions. This is the advantage and disadvantage of the fully associative mapping. Up next, the advantage and disadvantage of the set associative mapping. The advantages of set associative mapping: balanced, compromise, and disadvantages is complexity. The advantage is that the set associative mapping strikes a balance between the simplicity of direct mapping as well as the fully, the flexibility. These are the advantages in those types, right? So this is including both of those. Reduce conflict misses by dividing the cache into sets. It mitigates some of the conflict misses associated with the direct mapping. So the disadvantage is that the complexity, although less complex than the fully associated mapping, set associative mapping still requires additional hardware. It is, even though the simpler than the previous mapping function, it is still more harder, and it still requires additional hardware for set indexing and searching within each set. Increased hardware cost. The hardware cost is very high, so that's why it is very complex. The extra complexity can result in a higher cost implementation compared to the direct mapping. This is the advantage and disadvantage of a set associative mapping. Let us compare the three types of mapping functions: the direct, fully associative, and set associative. It highlights the specific cache lines associated with the memory blocks, and the fully associative mapping illustrates the unrestricted placement of the memory blocks within the cache. And the set associative mapping depicts the grouping of cache lines into sets and corresponding memory block placements. These are the comparisons of all the three mapping functions. And even let us know what is the impact of these mapping functions on the cache performance. The direct mapping may lead to the higher cache misses, right? That is disadvantage in the direct mapping, and longer access times for certain memory access patterns. So the performance will be very much low in the direct mapping because there is an occurrence of the cache misses. In fully associative mapping offers efficient data placement but requires additional hardware resources for tag comparison. Next, this is associative mapping balances flexibility and hardware complexity, leading to improved cache performances in many scenarios. These are the impacts on the cache performance. Now we will know what is the real-time advantage of these mapping functions. Around 1K products, they are used in the enterprise servers, the embedded systems, as well as the computing, cloud computing. So that is the use of the mapping functions in the real world application. We are at the last slide of our video. Let us conclude this with the few takeaways. The maintain balance, consider application, and continuous optimization. Each mapping functions offers a unique balance of flexibility and hardware complexity. Even though we have certain disadvantages, it also has somewhat advantages, and it is more some mapping functions are flexible and more highly accessible, right, compared to other. So this is about maintaining the balance. Next, consider application. The choice of mapping function should be aligned with the specific performance requirements and memory access patterns. So during the application where we are using, it depends on that, okay, which mapping function we have to use. That depends on which application we are using. So that is, we have to decide, we have to consider which mapping function we require for the application for which we have to use. Next, continuous optimization. Cache memory design is an evolving process requiring continual evaluation and refinement. So we need to modify, the refinement will be taking place, that is a evolving process that will be evolving forever, like that will be modifying from day to day. So this is the continuous optimization of the the mapping functions. So these are all the cache memories, how the data is stored, retrieved, what are the processes taking place when the data is present in the cache memory and when it is not present, like cache misses and the cache misses and cache, and the mapping function, the types of mapping functions, what are its impact on the cache memory performance, and at last the key takeaways and even the real world applications of the mapping functions. So thank you for being up to here. I thank Maya ma'am for giving us this opportunity to share our knowledge with all of you. Thank you so much for patiently hearing me until here. Thank you so much.